Dear students, this is third lecture on the topic magnetic effect of electric current. In this lecture, we are covering two topics, theory and working of moving coil ballistic galvanometer, and other one is the figure of merit of this BG and its determination. It's a lengthy lecture, so I will split this lecture into two videos. In first video, I will cover theory and working of moving coil ballistic galvanometer. So, you already learned about the moving coil galvanometer in your plus 2 classes, where you studied not the moving coil ballistic galvanometer. Instead, you studied moving coil deadbeat galvanometer. Here, we are studying the moving coil galvanometer, but different from what you learned in plus 2. The galvanometer used here, this ballistic galvanometer, is used to estimate the amount or quantity of charge flowing through it. There you used to measure the deflection, when there you used to measure the current. Okay, here in this galvanometer, using this moving coil galvanometer, what we do is we measure or we estimate the amount or quantity of charge that is flowing through that galvanometer. Okay, there you detected the deflection. If the current is flowing to the leftward, the needle will goes to left side, deflection. You will get a deflection to leftward, and if the current is flowing to rightward, you will get a rightward deflection. അതായത് നമ്മൾ പ്ലസ് 2-ൽ എന്ത് പഠിച്ചിട്ടുണ്ട്? മൂവിംഗ് കോയിൽ ഗാൽവനോമീറ്റർ പഠിച്ചിട്ടുണ്ട്. എന്താണ് അവിടെ പഠിച്ച ഗാൽവനോമീറ്റർ? അവിടെ പഠിച്ച ഗാൽവനോമീറ്റർ നിങ്ങൾ എന്താ ചെയ്യുന്നത്? നിങ്ങൾ അവിടെ പഠിച്ച മൂവിംഗ് കോയിൽ ഗാൽവനോമീറ്ററിന്റെ പ്രിൻസിപ്പളും ഇതിന്റെ പ്രിൻസിപ്പളൊക്കെ സെയിം ആണ്. പക്ഷെ ഇവിടെ ഒരു ഡിഫറൻറ്റ് ഉണ്ട്. അവിടെ നമ്മൾ ഗാൽവനോമീറ്റർ, അത് ഏത് ഗാൽവനോമീറ്റർ ആയിരുന്നു? ഒരു ഡെഡ് ബീറ്റ് ഗാൽവനോമീറ്റർ ആണ്. അതിന് ഓസിലേഷൻ ഇല്ലാത്തൊരു ഗാൽവനോമീറ്റർ ആയിരുന്നു. ഓക്കെ, അവിടെ എന്താ സംഭവിക്കുക? കറണ്ട് കൊടുത്തു കഴിഞ്ഞെങ്കിൽ ലെഫ്റ്റിലേക്കാണ് കറണ്ട് ഫ്ലോ എങ്കിൽ ലെഫ്റ്റിലേക്ക് ഡിഫ്ലക്ഷൻ കാണിക്കും, റൈറ്റിലേക്കാണെങ്കിൽ റൈറ്റിലേക്ക് ഡിഫ്ലക്ഷൻ. അപ്പോൾ നമുക്ക് കറണ്ട് ഒരു സർക്യൂട്ടിൽ ഉണ്ടോ എന്ന് നോക്കാൻ ഉപയോഗിക്കുന്ന തരം ഒരു ഗാൽവനോമീറ്റർ ആയിരുന്നു അത്, അല്ലെ? അതിനെ നമുക്ക് അമ്മീറ്റർ ആക്കാനും വോൾട്ട് മീറ്റർ ആക്കാനൊക്കെ നമ്മൾ പഠിച്ചിട്ടുണ്ട്. ഇവിടെയുള്ള ഈ മൂവിംഗ് കോയിൽ ബാലിസ്റ്റിക് ഗാൽവനോമീറ്റർ എന്ന് പറയുന്നത് ഇതും ഒരു എന്താണ്, മൂവിംഗ് കോയിൽ എന്ന ആ ഒരു കോയിലിന്റെ മൂവിംഗിന്റെ പ്രിൻസിപ്പിൾ തന്നെയാണ് ഉപയോഗിക്കുന്നത് ഈ ഗാൽവനോമീറ്റർ. പക്ഷേ ഈ ഗാൽവനോമീറ്റർ നമ്മൾ യൂസ് ചെയ്യുന്നത് എന്തിനു വേണ്ടിയിട്ടാണ്? ചാർജ് എസ്റ്റിമേറ്റ് ചെയ്യാൻ വേണ്ടിയിട്ടാണ്. എത്ര ചാർജ് അതിലെ കൂടി നമ്മൾ കടത്തി, അല്ലെങ്കിൽ നമുക്ക് ആ ഗാൽവനോമീറ്ററിൽ കൂടി കടത്തിവിടുന്ന ചാർജിനെ എസ്റ്റിമേറ്റ് ചെയ്യാൻ നമുക്ക് ഇത് ഉപയോഗിച്ച് പറ്റും, ഈ ഗാൽവനോമീറ്റർ വെച്ച് പറ്റും. Okay, so galvanometer used to estimate the amount or quantity of charge flowing through it is called moving coil ballistic galvanometer. In this case, the charge passed through the galvanometer is always proportional to the deflection of the coil. ഈ കോയിലിനകത്ത് ഈ ഗാൽവനോമീറ്ററിനകത്ത് നിങ്ങളൊരു കോയിൽ ഉപയോഗിച്ചിട്ടുണ്ടാവും. ആ കോയിലിലെ കൂടി കടന്നു പോകുന്ന ചാർജ് എന്തിന് പ്രൊപ്പോർഷണൽ ആയിരിക്കും? ആ കോയിലിന്റെ ഡിഫ്ലക്ഷന് പ്രൊപ്പോർഷണൽ ആയിരിക്കും. ഓക്കെ, അത് വെച്ചിട്ടാണ് നമ്മൾ ഇതിന്റെ പ്രിൻസിപ്പിൾ പറയുന്നത്. ഓക്കെ, അപ്പം യൂഷ്വലി നമ്മൾ ഒരു ഇൻസ്ട്രുമെന്റിനെ കുറിച്ച് പറയുമ്പോൾ അതിന്റെ പ്രിൻസിപ്പിൾ പറയും, കൺസ്ട്രക്ഷൻ പറയും, വർക്കിംഗ് പറയും. ഓക്കെ, ഡയഗ്രാമും നമ്മൾ കാണിക്കുന്നുണ്ടാവും. അപ്പോൾ അതേ പ്രൊസീജിയർ തന്നെയാണ് നമ്മൾ ഇവിടെ യൂസ് ചെയ്യുന്നത്. സോ വി വിൽ ഫസ്റ്റ് സീ ദ പ്രിൻസിപ്പിൾ, ദെൻ വി വിൽ ഗോ ടു ദ കൺസ്ട്രക്ഷൻ, ദെൻ വി വിൽ സീ ദ വർക്കിംഗ് ഓഫ് ദിസ് ഗാൽവനോമീറ്റർ. ഓക്കെ, സോ here I gave the picture of that ballistic galvanometer. You might have seen in your laboratory. Okay, anyway, you are going to perform the experiment using this instrument in your future class. You can see that the setup includes this one box type instrument, like it is a box in a case, and it has a level screw and all. And along with that, we have a scale and a light arrangement. This both is needed for the measurement to perform using this ballistic galvanometer. അപ്പം ഈ ബാലിസ്റ്റിക് ഗാൽവനോമീറ്ററിന്റെ കൂടെ നമുക്ക് ഇതുപോലത്തെ ഒരു സെറ്റപ്പ് ഉണ്ടാവും. അത് നമ്മൾ കേസിനകത്താണ് അടച്ചു വെച്ചിട്ടുള്ളത്. ഇവിടെ ഇതിനകത്ത് നിങ്ങൾ നോക്കുകയാണെങ്കിൽ, ഇവിടെ നോക്കുകയാണെങ്കിൽ ഒരു മിറർ കാണാം. മിററാണ് നമ്മൾ പിന്നെ പറയാൻ പോകുന്നത്. ഈ മിററിലോട്ട് നമ്മൾ എന്ത് ചെയ്യുന്നത്, ഈ ഒരു ലൈറ്റും സ്കെയിലും സെറ്റപ്പ് കണ്ടില്ലേ, അവിടുത്തെ ആ ലൈറ്റ് ഈ ലൈറ്റ് നമ്മൾ ഇതിന്റെ ഉള്ളിലേക്ക് ഫാൾ ചെയ്യുന്നുണ്ടാവും. ഈ മിറർ നമ്മളൊരു ഈ കോയിലുമായിട്ട് അറ്റാച്ച് ചെയ്ത് അതിനെക്കുറിച്ച് ഞാൻ പിന്നീട് പറയുന്നുണ്ട്. അപ്പോൾ ഈ ലൈറ്റ് സോഴ്സിൽ നിന്ന് വരുന്ന ലൈറ്റ് ഈ മിററിൽ വീണിട്ട് ഈ മിററിൽ ഉണ്ടാകുന്ന മോഷൻ, ഈ മിററിന്റെ ഡിഫ്ലക്ഷൻ ആണ് നമ്മൾ എവിടെ മെഷർ ചെയ്യുക? ഈ സ്കെയിലിൽ മെഷർ ചെയ്യുക. ഓക്കെ, അപ്പം ഇതിന്റെ കൂടെ ഈ ഒരു ബോക്സ് ടൈപ്പ് കൂടാണ്ട് ഇതിന്റെ കൂടെ എന്തുണ്ടാവും? ഒരു ലൈറ്റും സ്കെയിലും അറേഞ്ച്മെന്റ് ഉണ്ടാവും. അത് വെച്ചിട്ടാണ് നമ്മൾ ഇതിന്റെ മെഷർമെന്റ് ചെയ്യുക. അപ്പോൾ ഈ ലൈറ്റും സ്കെയിലും അറേഞ്ച്മെന്റും വർക്കിംഗ് പറയുന്ന സമയത്ത് നമ്മൾ പറയും. ഓക്കെ, നമ്മളിപ്പോൾ പറയാൻ പോകുന്നത് ഇതിനകത്തുള്ള സെറ്റപ്പാണ്. So we need this box type setup and also this scale and light arrangement. Using these we can perform the measurement of the charge that is flowing through this galvanometer. So both these setups are needed to do an experiment using moving coil ballistic galvanometer. Okay, so now we are going to see the construction inside this. And first we will say the principle used, then we will go to the construction, and I will remove this external box and we will see the inside setup. Okay, after removing that box, this is the inside setup that we are going to see in construction part. So first we will see the principle. Principle, you can either state the principle that you learned for a moving coil galvanometer in +2, that was when a current carrying rectangular coil suspended in a magnetic field, it will experience a torque. Okay, that is the principle that we learned for moving coil galvanometer in +2. But here we are simplifying that and we are telling that when a current is passed through a coil, either the same thing, when a current carrying rectangular coil is suspended freely in a magnetic field, it will experience a torque. That means we are going to the basic thing. If that force is acting, that force is causing the torque. Okay, that is what we learned in +2. But here we are simplifying it and we are saying that when a current is passed through a rectangular coil or a coil that is suspended freely in a magnetic field, it will experience a force. The direction of force is given by Fleming's left hand rule. Either you can use this as principle, you can state this one as the simple statement as the principle, or you can state the other one that the current carrying rectangular coil suspended in a magnetic field experiences a torque. Both are equally good. Any of that you can state as principle. Okay, and I am quoting this because this is the statement that is given in your text for study. Okay, and now we will go to the construction. So either of that you can choose. Okay, now we are going to the construction. So we are removing that box and we are seeing inside. The main part is the rectangular coil, because that rectangular coil, the most of the rectangular coil that decides our working. Okay, so the rectangular coil is made up of the thin copper wire. Okay, so we will take a thin copper wire and we will take a non-metallic frame that is in a rectangular shape. Okay, we will take a non-metallic frame. The non-metallic frame, either you can take a ivory, usually we will use ivory, or aluminum frame. That we will take in a rectangular form, so that we can wind this thin copper wire on that rectangular frame, so that we will get a rectangular coil. Okay, so how we are making a rectangular coil of thin copper wire? We are taking a non-metallic frame which is in the shape of the rectangle. So you will wind that thin copper wire on that non-metallic frame such that we will get a rectangular coil of thin copper wires of any turns. We will take that n turns. Okay, so what we did, we took a non-metallic frame of either ivory or aluminum frame that is in a rectangular shape. On that you wound thin copper wire, so you will get a rectangular coil of thin copper wires of so many turns. Okay, and this one is suspended by means of, which is this rectangular coil is suspended by means of phosphor bronze wire. So here is our rectangular coil. So this is we wounded on a, we are seeing from upper side. Okay, we are seeing from a top to bottom. So you are seeing from a top to bottom, so you are getting this view. Okay, you are seeing from top to bottom to inside to that. So here is this one, these things, not this dark, this C. This is different thing that we will say later. So these are not that dark one, other things. These are our rectangular coil. Okay, this rectangular coil is suspended by means of a phosphorus bronze wire. Okay, phosphorus bronze wire. That is an alloy. Okay, wire. And this is suspended between, this coil is suspended between these two poles of a horseshoe magnet, strong horseshoe magnet we are using. Okay, that is a cylindrical shape. We are getting a cylindrical shape. You are seeing from the top, that's why you are getting a curve like this. Okay, so what we did, we made a rectangular coil, and this rectangular coil is suspended between the strong poles of a horseshoe magnet by means of a phosphorus bronze wire. Okay, and a small mirror, concave mirror, a circular mirror is attached to the suspension wire. Okay, that mirror is observed here. Okay, that is here. Other things are there. Okay, and coil is coming here. Okay, so mirror is attached to this suspension wire, and the lower end of the wire, this is the lower end of the wire, is connected to a spring. Okay, and the lower end of the spring is connected to the terminal T2, and upper end of the wire is connected to the torsion head. Torsion head, that means it can move, it can rotate, and from there this is connected to a terminal T1. So through this we can apply the potential. Okay, so this is a setup. Here is a hair spring. Okay, that hair spring will give is a restoring torque, that we will see later when we are telling about the working. We will think about that. Okay, so we have this rectangular coil is suspended in between the strong poles of a horseshoe magnet by means of a phosphorus bronze wire, and there is a mirror attached to that suspension wire, and the top end of the wire is connected to torsion head. From the torsion head, that wire goes to terminal T1, and the lower end of our rectangular coil is connected to a hair spring. From the lower end of the hair spring, we are connected to T2, and through this we can give the potential. And one more thing that you have to see, that in between or inside that coil, we symmetrically place a cylindrical soft iron core. Okay, and that is placed between these poles of the magnet. That means if you have a frame, rectangular frame, if you think a rectangular frame, the rectangular frame, that what you are doing, you place a cylindrical iron core inside to that. Okay, if you have a rectangular frame, you place a cylindrical iron core to that. Okay, that iron core will place symmetrically inside that coil, and between the poles. Why it is placed? And this will concentrate the magnetic field and will produce a radial field. This iron core. This iron core will make the field from that center point, from the iron core, we will get all through the radius of a circle. Like field will be going like a through the radius of the circle from that center of the iron core. What's the advantage of that? Advantage of that is when wherever our this coil, rectangular coil moves, that coil will be always parallel to that field. The direction of the coil will be always parallel to what will we say, whichever direction it is aligned, the surface or that coil will be always parallel to that field, such that normal to the that coil will be always perpendicular to the radial field. Normal is important. That we will normal to the surface of the coil. Okay, so the coil will be our surface of the coil will be always parallel to the field that is produced. Okay, that means that field will always making a 90 degree with the normal to the surface of that coil. Okay, that's the important thing that is used when we are deriving our equations. So iron core concentrates the magnetic field and produces the radial field. That's the important thing. Radial field is needed. Radial field means like through the radius of the circle the field is going. That will help to maintain a parallel field along with the surface of the coil, and that means the normal, if you draw a normal to the surface of the coil, you will get it is always perpendicular to the magnetic field. Okay, that is the importance of radial field. And we use the coil of high moment of inertia here. Okay, why we are using high moment of inertia? If you have a high moment of inertia, you will see in later the equation that it will produce the maximum time period for the oscillation. Okay, to make the period of oscillation large, we are using the coil of high moment of inertia. Okay, we are using this coil of high moment of inertia. Okay, this is the construction. I think you got the construction. Okay. Now we will go to the theory and working of that. So we covered the principle, then we covered the construction. Now we will go to theory. Now we will consider that the rectangular coil that we made that what turns. Okay, I said here rectangular coil, that copper wire that we wound on non-metallic frame. We are considering that rectangular coil have n turns. We wound it n turns. Okay, and this is placed in a uniform magnetic field. Okay, now we are considering that the length of that rectangular coil, this we already learned in the previous lecture. Okay, we are considering that height or length as L and breadth as B. Okay, then we can say the area of this coil, a single coil I am telling now, is A equal to LB, area of that coil. Okay, and we learned that if we place this rectangular coil in a magnetic field, and if a current I passes through that, okay, if a current I passes through that, this coil will experience a torque. Okay, and now what we are saying is we are placed this coil in a radial field. That means the normal is making the normal to this rectangular coil is always perpendicular to this field. Okay, so angle between the field and the normal to the coil will be always 90 degree. Okay, if you take the torque on this coil, we got the equation that torque is equal to NIBA sin theta. That theta was the angle between the normal to the coil and the magnetic field. If you remember the previous class, there we explained what is theta. Theta was the angle between the normal to the coil, normal to the surface of the coil and the magnetic field. Okay, so here also it's a radial field. Radial field means the normal drawn to this surface makes an angle 90 degree with our field. Okay, if it is radial field means always it will make a 90 degree. So sin 90, that is 1. So what we will get is torque on the coil, which is having n turns and passing I current through that. Okay, you will get torque as NIBA sin 90. So NIBA remains. There NIA we took as mu. I think you remember that. We wrote as mu cross B. Mu was NIA. Okay, here it is in an elaborated form. Okay, now what we think is, it is important. We are passing a current for a short interval dt. That means you are passing you are passing current for a long interval. Suppose if you are passing a current through that coil only for short interval, what will happen? You are applying a torque for a short time. That means you are applying an angular impulse. Like what we learned, when you are applying a momentum for short interval, you used to get impulse in the linear motion. Here, what we are doing, we are passing current for a short interval dt. That means you are creating a torque for a short impulse. There, if you act a force for short time, you will get an impulse in a linear motion. Yes. Here, what we are doing, here we are passing this current for a short interval. That means you are applying only torque for a short interval. That means you are giving a short angular impulse to that coil. Okay, so how there you used to get impulse as force into time. Here also, this the short angular impulse produced by the coil, we can write as tau dt. Here is angular. So torque means you will get only angular. Here is impulse means here is angular impulse. So angular impulse produced in the coil for a short interval of time dt, the current passes for only short interval dt. We are considering like that. So there will be an angular impulse. That angular impulse we can write as tau dt, that is equal to NIBA dt. But if we think that this current is passed for t seconds, we talk that first we are telling that if the current is passed only for short interval dt, so there is a short angular impulse. But if we pass this current for t seconds, then we can get the total angular impulse given to the coil. We are thinking that we are passing the current through that coil for t seconds. So total angular impulse given to the coil due to the current passing through that coil for a time period of t is equal to what you can do, you just integrate that from 0 to t. Okay, 0 to t tau dt will give the total angular impulse given to that coil for a time period of t seconds. So that is equal to what you can write. You can see here N, B, A are the constants that relate to the field that we applied. N is number of turns. A is the area that is not changing. Only what is changing here is the current that is passing through that. Okay. So with time the current increases, or the variable that we will get here is IDT. Okay, with time, okay, I will change. Okay, that you have to integrate. And we know that I is dq by dt. Okay, I is dq by dt. Okay, IDT what you will get dq. I is equal to dq by dt. If you know that I equal to dq by dt. Dt goes here IDT means dq. So here it actually remains dq. If you integrate that, you will get q. What is q? Q is the total charge that is passing through the galvanometer coil for a period of t seconds. That means that much time only you pass the current. So due to that current, how much charge is passed through that galvanometer, that we will get by integrating IDT from 0 to t. So instead of IDT, you can put Q. Okay. So what we got? We got that if a current passes for t, if a current I passes for t seconds through that n rectangular coils of n turns, you will get the total angular impulse given to that coil as NVAQ, where Q is the total charge that is passed through the galvanometer coil due to the current that is passed through it for t seconds. Okay. So this is the first expression. Now let I be the moment of inertia of the coil. Okay, moment of the inertia of the coil about the axis of suspension. It is suspended. Axis of suspension. Okay. Before you are applying the current, that coil is remaining stationary. So its angular velocity is 0. You know that its angular velocity is 0. When you applied the current, it got an angular impulse. Due to this angular impulse, it started moving. Okay, it started rotating. Okay, so when it started rotating, it will have an angular velocity. So due to this current I, it got a velocity, angular velocity omega. Okay, so what is the change in angular momentum of the coil? Change in angular momentum of the coil is I omega minus I into 0, because initially it was 0. So change in the angular momentum of coil is I omega. Change in the angular momentum of the coil is I omega. This change d by dt of I omega, or change in d by dt, not d by dt, the change in the momentum of the coil, that is d of I omega. D of I omega, okay, d of I omega will be always equal to total angular impulse. Total angular impulse. Why? Because d by dt of I omega is tau. D by dt of I omega is tau. You know that d by dt of angular momentum will give you torque. Okay. dp by dt gives you force. dp by dt. So here d with angular momentum, okay, d I omega by dt should give you torque. You learned that in +2, that will give you torque. If tau dt, that is tau dt if you take tau dt, you will get is I omega. Here integration will come in place, okay, because we talked about the total change here. I omega means I0 all we took. So here what you got, integral 0 to tau dt will be equal to I omega, change in angular momentum. We can say that. Okay, how you are relating, you are getting, I think. Okay, so change in angular momentum of the coil, that is d of I omega, is equal to integral 0 to t tau dt, that will be equal to NEB. Okay, this is the relation. How we got that total angular impulse in terms of change in angular momentum of the coil, because that coil is getting an angular impulse. So it will always, it will twist, it will experience a torque. So torque into dt, we can relate that to an change in angular momentum of the coil. That change in angular momentum will be, okay, change in angular momentum of the coil is I omega. That I omega will be always equal to NEB AQ. NEB AQ. That is the first equation that we got. This same thing you can think of as how we use the linear force and linear momentum. Same way it will come here also. There also you can relate that to impulse. Same way here we can relate to angular impulse. Okay, so we will get I omega is equal to NEB AQ. That's the first equation we are keeping. Now we will proceed like, since this coil is moving, that suspension wire will get twisted, or spring will also get twisted, because coil will start rotating. As the coil rotates, okay, suspension wire will also get twisted, and we are thinking that this suspension wire is twisted through an angle theta due to the rotation motion of the coil. Okay, definitely at the bottom there is a spring. That spring will introduce a restoring torque into that system. So this suspension wire, which is twisted by this torque, will have also a restoring torque which is opposing this rotation motion of the coil. Okay, if the suspension were twisted through an angle theta due to the rotation motion of the coil, there will be an restoring torque that is developed in the suspension wire due to that the spring that we have attached at the bottom, that will make it that rotation to stop at a vertical point. Okay. So if C is the restoring torque per unit twist of that suspension wire, we are telling about the suspension wire. Okay. If the C is the restoring torque per unit twist of the suspension wire, okay, the work done in twisting the suspension wire to angle theta, you will get that as theta square. How we are getting that? What we are saying, we are telling that this suspension wire is twisted through an angle theta due to the rotation motion of the coil. Okay. Actually, when it is rotating, the spring that is attached at the bottom, that will produce a restoring torque, that will introduce a restoring torque into the system. So this suspension wire will be having a tendency to oppose this twisting. Okay, we are telling that if C, we are considering that if C is the restoring torque per unit twist of that suspension wire, that means you have to do work to overcome that restoring torque. Okay, so how much work you have to do to twist it through an angle theta? That means C theta will give you that idea of that twist. Okay, so work done will be, you are twisting through an angle theta, so work done will be integral 0 to theta C theta d theta. C theta d theta, because C is the restoring torque per unit twist. So how much twist is there? Theta angle twist is there. So how much restoring torque is there? C into theta. So if you want to do a small, small work to twist through angle d theta, means that is dW is equal to c theta d theta here. So how much work you have to do to twist this angle, this wire through angle theta, means you have to integrate it from 0 to theta, c theta d theta. Okay, if you are, that is the basic thing. And what we have to know is that the suspension wire is twisted to angle theta. Because there is a restoring torque developed in that suspension wire, you have to, in order to rotate it to an angle theta, you have to do work. Okay, how much work you have to do? You have to do work. How much work if you have to do? That work you have to do is integral 0 to theta, because you are twisting up to theta. C is the restoring torque per unit, so C into theta, because you are rotating it through an angle theta. That is C theta d theta, integral 0 to theta, C theta d theta. If you do that, you will get integration. You will, after the integration, that work done for twisting suspension wire through an angle theta, you will get it as half theta square. Okay. So work done twisting the theta, work done in twisting suspension wire will be always equal to kinetic energy of the moving coil, because this moving coil, that the coil which got an angular impulse and it started moving. So when it started moving, it will have a kinetic energy. There is a rotational kinetic energy. This rotational kinetic energy of the moving coil is utilized to twist that suspension wire through an angle theta. So the kinetic energy of the moving coil is converted into the work done in twisting the suspension wire. So we can compare that. That will be equal. Okay. So what we can write? The work done half c theta square will be always equal to half I omega square, the kinetic energy in the rotational motion. If I is the moment of inertia, omega is the final velocity, then half I omega square. Okay, is the kinetic energy of that moving coil. That means you can cancel half and half, you will get I omega square is equal to c theta square. This is equation 2. Now we want to simplify and get an equation for Q using equation 1 and 2. Using equation this 1 and 2, we want to simplify and get an equation for Q. Okay, for that we are doing some more steps. So in this case, if you take the period of oscillation of the coil that we are directly taking, if you find the equation in some other textbook, you can find that equation for time period. Okay, we are directly taking period of oscillation for coil. If it is having I as the moment of inertia of that coil, and that suspension wire is having the restoring torque per unit as C, we will get T is equal to 2 pi root of I by C. 2 pi root of I by C. Okay, for that system. That system, whatever we talked in the construction, for that the period of oscillation of that rectangular coil, you will get T is equal to 2 pi root of I by C. I is the moment of inertia of that coil. Okay, C is the restoring torque per unit of the suspension wire. And if you square that, you will get T square is equal to 4 pi square I by C. And from there I can take I. Then I is equal to T square C divided by 4 pi square. Okay. Now what we will do is we will multiply equation 2 and 3. Then the I into I omega square, that means I square omega square, is equal to the other side T square C square, T square C square theta square divided by 4 pi square. We just multiplied the left hand side and right hand sides of the equation 2 and 3. Okay, now we can take the root of that. If you take the root of that, you will get I omega is equal to Tc divided by 2 pi. Okay, Tc divided by 2 pi into theta, sorry. I omega is equal to Tc theta by 2 pi. Now we will compare the equation 1 and 4, because the left hand side of the equation 4 is I omega and the left hand side of the equation 1 is I omega. So I can write NEBAQ is equal to Tc theta by 2 pi, and just putting it as Ct theta by 2 pi. Okay, so we just comparing, because the left hand side for the equation 1 and equation 4 is I omega. So I can write it as NEBAQ is equal to Ct theta by 2 pi. Or right hand sides are compared of equation 1 and equation 4. Now I place Q here and I will rearrange there. So I am first putting T by 2 pi as one term, and then I am putting C by NBA. C by NBA as other term, and theta. Why? Because this T by 2 pi, C, NBA all are constants for a particular that materials and the field whatever we are telling. So we will get Q is proportional to theta because this is constant. Or I can write Q is equal to K theta, and this K, T by 2 pi C by NBA, is called ballistic reduction factor or charge sensitivity or figure of merit of BG. Whatever I told the figure of merit, we are going to learn that figure of merit is now this K, or the figure of merit of BG. And this equation Q is equal to K theta, gives the relation between charge flowing through the ballistic galvanometer and the angle produced, the twist produced, the theta, ballistic throw, we will say it as ballistic throw of the BG. Okay. So this is the theory that we want to learn. So working, this working is already came here. We will tell once again. So how it will work? We will go to this figure. When we pass the current through this one, a torque is developed in this coil. Okay, and because we are sending the current for a short period of time, we are putting an impulse. Due to that, what will happen? It will experience an impulse and started twisting. When it started twisting, this mirror will also twist. Okay, this started rotating. When it started rotating, the mirror will start also rotating. It will twist due to the restoring couple. This gives to this one. This setup will have also a restoring couple. Okay, so restoring torque. That restoring torque per unit twist we can take it as C. So when it is rotating, this mirror is rotating. What we did? We are placing this setup in front of this one, so that when this light falls on this mirror, first when you are not sending the current, that will coincide with 0. When you send the current, when it started twisting, what is twisting? Our suspension wire is twisting and coil is moving. That time this mirror will also get deflected. When it is deflected, so the light will either move to, when it is go to left, it will go to left, and when it goes to right, it will go to right. So deflection means it gives an oscillation, sudden oscillation. That means it will oscillate like this, First it will go to higher value, then lower value, lower. Last it will be dead. So that throw that will get, because when current passes, this suddenly it will experience, that coil will experience a torque. When it is experience a torque, it started rotating. When it started rotating, the suspension wire twisted. Twisting time this that mirror will get twisted, or mirror started deflecting. When it started deflecting, the light which falls on that mirror also moves like it oscillate. Okay, oscillate to both sides. That reading we will get on the scale. In millimeters we used to measure the deflection. Okay, it will goes to this side, like this. It will go. Details we are learning when we are telling about its current sensitivity and voltage sensitivity, also figure of merit. That time also we have to learn how this works. And now we will go to one more thing in the theory, that is correction for damping. Why we need a correction for damping in this case? Whatever moving coil ballistic galvanometer, what we think is it is having what? This damped, it is having no damping. Damping force is not there. It is an ideal case. That means whatever the kinetic energy is coil is having, that is used to twist the suspension wire. We are thinking like that. That means there is no damping. There is no damping force. What will cause the damping? Usually damping will be caused by a resistance. What is damping? Damping means the resistance for that motion, proper motion of that coil. Okay, we are thinking that coil is free to move. Which coil? The rectangular coil. Whatever that torque, whatever impulse it gives, that impulse is used for it will produce kinetic energy. That kinetic energy is used for twisting the suspension of the coil. We are thinking like that. That means damping is not there. There is no restriction for the motion of the coil. We are assuming like that in the case of an ideal moving coil ballistic galvanometer. Actually, that not be the case. The whole kinetic energy given to the coil cannot be used to twist the suspension of the coil, because this motion of the coil is blocked by the air resistance, also some current induced in that coil. So the whole kinetic energy can be used for twisting suspension coil. So what's the problem? The problem is that we equated thinking that the whole kinetic energy is used for twisting the suspension wire. So our equation is Q T by 2 pi C by NBA into theta can't be right, because this Q that we got by assuming that our entire kinetic energy used for twisting an angle theta. That means this won't be theta, there should be correction for theta. That correction for theta is known as the damping correction. Okay. So actually the first throw of the galvanometer, that's what we are telling as theta, will be smaller than it would be in the absence of damping. Okay, that means we got the theta thinking that there is no damping. Actually, this theta will be less than whatever we are getting for an ideal case. So we have to modify for this theta. That is what we are doing, this damping correction. So first throw of the galvanometer will be smaller. Why? Because of damping force that damps the motion of the coil. So we have to correct for the value of the first throw. Okay, that's what we do in damping correction. Okay, so we are doing damping correction. Damping correction means we are accommodating that this kinetic energy is not completely used for twisting of the suspension coil. There is some damping problem due to air resistance and the induced current. Okay, so what we are thinking is, let this theta 1, okay, then we are going to theta 2, theta 3, theta 4, theta 5 are successive maximum deflection from zero position to the right and left. Theta 1 to the maximum to the right, then theta 2 the maximum to the left, then theta 3, this is right maximums and these are left maximums. Successive maximum deflection from zero position to right and left as shown in the figure. Okay, then what is observed experimentally that if you take the ratio of theta 1 from 0 to this theta 1 by theta 2 and you take theta 2 by theta 3, then you take theta 3 by theta 4, all these found to be equal. If you take theta 1 by theta 2, that is the deflection, the maximum deflection to the right divided by the maximum deflection to the left, successive, okay, successive maximum deflections, right and left, the ratio of that, you will find that theta 1 by theta 2, this the ratio of successive maximum deflections to right and left is found to be a constant. That you are getting as constant and we are putting that as D. Okay. So experiment is observed that the ratio of successive maximum deflection to right and left is a constant. The constant we are marking as D and it is called as decrement for half vibration. Why it is called decrement for half vibration? You see, that means theta 1 is here. So from theta 1 to you are moving to theta 2. Okay. And full deflection will complete when it comes to this side. So it won't come to theta 1, it will come to theta 3. So when you are moving from theta 1 to theta 2, you are moving half oscillation. You are doing an half oscillation. When it comes to theta 3, it will be full oscillation. I am starting from theta 1. So when we think that this oscillation, this deflection which is moving from this theta 1 to theta 2 makes a decrement, that decrement value, you will get theta 1 by theta 2, that ratio. You are getting a decrease in the value of the deflection. That decrease, that decrement, we can tell it as it is for an half vibration. Yes, because you are going to theta 1 to theta 2. And if you come to theta 3, that is full vibration. We are going to half vibration. So, in that half vibration, there is a decrement in the deflection. That decrement we can get by taking a ratio theta 1 by theta 2. Okay, if you take theta 2 to theta 3, that is also an half vibration. Because if it comes to theta 4, it will be a full vibration from that side. So, if you take theta 2 by theta 3, also you are getting a constant value that is also equal to theta 1 by theta 2. So, we can tell that ratio as decrement per half vibration. Okay, we will make that to logarithmic scale. For that, we will put d is equal to e raised to lambda. Then we can define lambda. Lambda is ln d. So, lambda is called a logarithmic decrement. Okay, we are making to logarithmic decrement. So, if you think for a complete vibration, that means you have to go from theta 1 to theta 2, then come to theta 3. So, complete vibration means theta 1 by theta 3. The ratio of that deflection for a complete vibration is theta 1 by theta 3. That you will get theta 1 by theta 3. You can split it as theta 1 by theta 2 into theta 2 by theta 3. Because theta 2 and theta 2 we can cancel. Theta 2, theta 2. So, for a complete vibration, you will get d into d square. D square means e raised to 2 lambda. E raised to 2 lambda. Okay. This we are doing because we are going for another argument that you have to carefully listen. Listen carefully. Okay. So, next argument you should listen carefully. Let theta be the true first throw in the absence of damping. We are assuming that this theta is the true first throw in the absence of damping. Because by thinking like that only we derive that equation. Okay, and we know that theta is greater than theta 1 because when damping comes, it goes to only theta 1. That means the first throw which actually should go to theta, it is only going to theta 1. That means in the quarter vibration, you are getting a decrement. That means instead of theta, you are going to theta 1. So what we can say is, after a completing quarter vibration, because you are starting with 0, you go to this side, you come to 0, you go to this side, you come to 0. That is a full vibration. If you start from 0, okay, you go to theta 1, go to 0, go to theta 2, come here. That is full vibration for that. Okay, so if you think like that, when it is doing a quarter vibration, actually if there is no damping, it will go to theta. But because of damping, instead of that, it is coming to theta 1. That means it is moving only quarter vibration. In that quarter vibration, it should go to theta, but it is decreased to theta 1. So what we can write is theta by theta 1. Okay, it should go to theta, but when it is completing quarter vibration, it is coming to theta 1. That means there is a decrement. There is a decrement coming by completing quarter vibration. So, the same way what we write for theta 1 by theta 2, we can write theta by theta 1. What is theta by theta 1? Theta by theta 1 is for quarter vibration. For half vibration, it is d. So, theta 1 by theta 2 for complete vibration. Theta by theta 1 is for quarter vibration. This is for half vibration. Theta 1 by theta 2 for quarter vibration. That should be half of this. This is half. Quarter means half of this. So, theta by theta 1 I can write as d by 2. I think you got the argument. How we are telling that? Actually, theta is a 2 first throw. But what is happening? This one is only going to theta 1. That means when it is completing a quarter vibration from 0 itself, instead of going to theta, it is coming to theta 1. So if you take the theta by theta 1, this is the ratio of deflection for half, not half vibration. This is quarter vibration. So if I can write ratio of deflection for half vibration as d, ratio of deflection for quarter vibration I can write as d by 2. So I am writing it as d by 2. Okay, so d is e raised to lambda, d by 2 is e raised to lambda by 2. I can write this e raised to lambda by 2. And I am just expanding it. E raised to x, I can write as 1 plus x by 1 factorial plus x square by 2 factorial plus x cube by 3 factorial. Higher terms I can neglect. So here 1 plus lambda by 2 1 factorial plus lambda by 2 whole square by 2 3 factorial, that I am that things I am 2 factorial, lambda by 2 whole square by 2 factorial, that things I am neglecting. So I can write just 1 plus lambda by 2. So we will get theta by theta 1 as theta by theta 1 is 1 plus lambda by theta equals theta 1 into 1 plus lambda by 2. Actually, we will get only theta 1. But our actual theta, if you want to get actual theta, you should multiply it with 1 plus lambda by 2. So, instead of, because of damping, instead of theta, we got theta 1. So, actual value, if there is no damping, we should put as theta. So, we can do the correction here. Instead of this theta, I can put theta 1 into 1 plus lambda by 2. Okay, theta, because we can't measure theta, we can measure only theta 1. In the equation we need theta. So instead of theta, what we are able to measure theta 1. So we will put theta 1, but theta 1 is less. So that theta 1 is equal to theta. Theta 1 is equal to theta if you multiply it with 1 plus lambda by. That's correction we got from here. So damping correction. How we go to the damping? When damping comes, instead of theta we will get theta 1. How we can go to from theta 1 to theta? You just multiply it with 1 plus lambda by 2. Now what is lambda? How we can get lambda experimentally? Okay, instead to get theta, you should get lambda. So how we will calculate lambda? That can be obtained. You take theta 1, you take theta 1 or theta 3. You just measure theta 1 and theta 3. You take the ratio of theta 1 and theta 3. You will get the value for lambda. But for getting more accurately, what we used to do, we will measure first row theta 1, then we will take the 11th row. That is not that you can take 6th or 7th or anything you can take, but usually for more accuracy, we will first measure the first row, then you measure the 11th row. Then you take the relation theta 1 by theta 11. That you can write as theta 1 by theta 2 into theta 2 by theta 3 into theta 3 by theta 4 into theta 4 by theta 5, like that into theta 10 by theta 11, because all this will cancel. All this will cancel. Only remain theta 1 by theta 11. But you will get 10 values. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 ratios. That means these all are D's. D into D into D into D. 10 D's. D raised to 10. D raised to 10 means D is e raised to lambda. So D raised to 10 means e raised to 10 lambda. E raised to 10 lambda. So you take a logarithm this side. ln of theta 1 by theta 11 is 10 lambda. So lambda is equal to 1 by 10 ln of theta 1 by theta 11. Or in terms of base 10, 2.303 multiplied 2.303 by 10 log, this is base 10. Okay, theta 1 by theta 11. You will get a lambda. Now you can get Q. In K theta, we can measure theta 1 and then we can go to theta. How we can go to theta? Theta 1 into 1 plus lambda. This is the corrected equation. Okay, this is the corrected equation. This will give you the value of charge that is flowing through that galvanometer for a ballistic throw, first ballistic throw theta. But we are getting a theta 1, we will go to theta. So this is the equation that we used to get the charge that flows through galvanometer when a current is passed through that. Okay, by measuring the ballistic throw or the deflection of that coil. Okay, deflection. Actually, deflection of the coil is measured by the deflection that we observed in the scale. With this, we will wind up here, and the remaining things I will talk in the second video because it will be very lengthy otherwise. Thank you for listening.